Chapter 12, Solutions, Section 12.1, Solutions. Big idea throughout this entire chapter are intermolecular forces. So what we saw in Chapter 11, we're going to use and apply here in Chapter 12. Even though we did apply the idea of intermolecular forces in boiling point, melting point, that kind of stuff, here we're going to see it in terms of solution. So what exactly is a solution? It's considered a homogeneous mixture. And so just to review that idea of homogeneous, here's a beaker of water, right? And if I put salt, table salt, into that water, sodium chloride, and I make sure it all dissolves, then the top of the solution has the same composition as the bottom of the solution. So that's a homogeneous mixture. The solution is the same throughout. Now it consists of a solute and a solvent. The solute is the substance that's being dissolved. We usually have less of that. And the solvent is the species doing the dissolving. Okay? So in our example of salt and water, water is our solvent. Salt would be our solute. Okay? Very important terms to know and to understand. So the solution typically has the same state as the solvent. And here you can see here are some examples of a solution. Okay, it doesn't have to be just a solid in a liquid. It can be a solid in a solid. It can be a liquid, solid, liquid. Right? So we know that water is polar. Okay, we learned that earlier. And so it's a polar solvent. It has very strong hydrogen bonding, and that is one of the reasons why water is a universal solvent. So it's the most common solvent because it does have that really strong hydrogen bonding. You'll see where that comes into play here a little bit further down in the notes. So let's talk about what actually happens in order for a solution to form. So as far as the forces of attraction between the solute and solvent, what are we talking about here? All right, well, there are three things that need to happen. All right. The first thing is we need to separate the solute from itself. So here's the solute. Let's say it's the sodium chloride. I'm just going to draw just a solid. So when I drop this solid into water, first thing that has to happen is we have to separate those particles from each other, which means that we have to weaken the intermolecular forces. All right. Now, if it's an ionic compound, we have to weaken the ionic bonds. So that's the first thing. We need to put energy into the system to separate those particles. Well, the solvent also needs to be separated, right? Because on the molecular level, for the solvent, there's no space between these particles, right? Because if there was space, there would be something there. Right? We're not going to create a vacuum right in the middle of our liquid, in the middle of our solvent. So we have to separate these particles from each other so that we can put one of these solute particles in there. Okay? It needs to fit right in there. So we need to separate the solute, we need to separate the solvent. Both of those things, we need to put energy into it. Bond breaking is endothermic, so we always have to put energy into a bond in order to break it. Bond making is exothermic, and so that's our next step, is we're going to release energy exothermic when the solute and solvent mix and form a force of attraction. So let's go back to our idea of the solute here. When that solute actually gets between these particles here, zoom this in a little bit. So when we actually take and we get that solute in the middle here, there is a force of attraction that forms, and that gives off energy. Okay. Now, in order for a solution to form, the energy has to be favorable. So how do we know that? Well, the attraction between the solute and solvent must provide enough energy in order to break that solute-solvent, or solute-solvent-solvent attraction. Okay, so we have to look at this in terms of, if we're looking at here, energy. Okay, so here's the solute-solute. It takes energy to break the solute-solute to get it to spread apart. It takes energy to break the solvent-solvent. And then finally, the solute-solvent attraction is going to release energy. Now if it just releases a little bit of energy like what we're seeing here, well then more than likely a solution won't form. If it releases a lot of energy to where it's exothermic, well more than likely our solution will form. Now this is a huge idea right here. If the solute and solvent have similar intermolecular forces, more than likely a solution will form. And we actually have a special phrase for this. It's like dissolves like. And there we're talking about the intermolecular forces. Similar intermolecular forces will dissolve other similar intermolecular forces. Now what that means for us is polar will dissolve polar substances, nonpolar will dissolve nonpolar substances, but polar will not dissolve nonpolar, and nonpolar will not dissolve polar. All right. So if the solution is polar-polar, we're going to have a solution. If the reactants are, if the solute and solvent are nonpolar, solution. Opposite, no solution. So what we see here in these pictures in letter A is CH2Cl2, which is nonpolar, and water, which is polar. So we have, here's the CH2Cl2, which is nonpolar, and then the water, which is polar. Well, they do not have similar intermolecular forces, therefore no solution. Okay? Now, here it's still CH2Cl2, which is nonpolar, but now we've taken and put iodine, solid iodine in there. Well, iodine is also nonpolar. So since iodine is nonpolar and CH2Cl is nonpolar, iodine dissolves into CH2Cl2. But here's water. Notice it's not purple. The iodine makes this purple. Water's not purple. Therefore, no iodine dissolves in water. Why? Because iodine is nonpolar. Water is polar. Like dissolves like. Those are not similar intermolecular forces. Therefore, they will not dissolve. They're not miscible or soluble. Miscible if it's liquids, soluble if it's not two liquids. Okay? So what about an ionic compound? Because we're talking about polar and nonpolar here. Well, an ionic compound, this is where we get those ion dipole forces of attraction that I talked about earlier in a previous video. So they dissolve, ionic compounds do dissolve in water because of similar attractive forces. And it's this ion dipole force of attraction. Okay, so if we look here, what's happening is that here's a water molecule. There's the negative end of the water molecule, right? The oxygen is the negative end. Well, it's attracting that positive. In this case, that's going to be the sodium ion. So what happens? If enough of those form enough attractions, enough water molecules form enough attractions to that sodium ion, it'll carry it off, which is what's called hydration. So it's a hydrated ion surrounded by waters. Here on the other side, we have that hydrogen, which has a partial positive charge, and it's attracting that negative chloride, right? And so we have something that looks like this, where all the positives are surrounding that negative. Now, let me just get a quick review here. Notice that sodium ion is small. The chloride ion is big. Well, the sodium ion lost an electron because it's a cation, and so it's going to get smaller because the nucleus has now an effectively stronger force of attraction holding fewer electrons. The chloride is going to get bigger because we have electron-electron repulsion, and the nucleus isn't attracting those outside electrons as strongly because there are more electrons to attract. So just quick review. So ionic compounds, when we put them in water, they dissociate. In other words, they break up. So here's sodium chloride breaking up into the sodium ion and the chloride ion. Let me show you another one. Right? Here's potassium phosphate, K3PO4. When I throw potassium phosphate in water, so water written over the yield symbol means that we're putting it into water. What am I going to get? I'm going to get 3 potassium ions and 1 phosphate ion. Okay, so they break up into their ions. Let me show you one more just because it's valuable to have this one. Let's say magnesium acetate. If I could write it, it'd be easier. Okay. When I throw magnesium acetate in water, which is an ionic compound, I'm going to get the magnesium ion plus 2 of the acetate ions. So again, it's important to know your polyatomic ions and your ions in general, because they will always break up into their ions. Alright? So don't break it up into, like a lot of times students will break this up into this. They'll do that, but that's not an ion. Right? That's not an ion. This is the ion. So that's ionic compounds. Now, polar molecules, they will dissolve in water, but they do not dissociate. And the reason why is because they are not made of ions. Okay? So here's methanol. Methanol is not made up of ions, so it can't break up into ions. So all it does, it just become aqueous. They become separated from each other. So here's methanol. Notice we have all these dipole-dipole forces. Those are hydrogen bonds. Here's water with hydrogen bonds. So we separate these from each other, separate these from each other. We slip a solute in between a solvent, and we end up with something like this. Okay, but again, they don't break up into ions. So that's a molecule. That's a covalently bonded molecule. Nonpolar solutes do not dissolve because there is little to no attractive forces between the solute and solvent. That's why they don't dissolve. There's also something that goes along with Gibbs free energy, but we don't worry about that just yet. We'll get into that later.